If we can find the derivative of a function, we say that it is differentiable. In this lesson, we're going to look at how we determine points where the derivative might not exist for a function. And we're also going to look at something called local linearity using derivatives. So first of all, we want to look at how the derivative might fail to exist. We're going to look at 4 instances where it won't exist, basically looking at the graphs. And one way this can happen is a corner where the two sides disagree. So for example, I have the graph of the absolute value function. On one side, my slope is -1, which means its derivative would be -1 on that side. It's equal to 1 on that side. Those two sides do not agree, so we don't know what's happening at that point. We would say that derivative does not exist, and we call this a corner. The next one looks like a corner, but it's actually a cusp. The difference with a cusp is that each side, or one of the sides, where either side is approaching a vertical line, but they are also going to point. This one is still continuous. On this one, we do have a vertical tangent line. It's also continuous, but there's no corner per se. It's still a smooth curve, and it's still connected. But at this point, we have a vertical tangent line. And so there would not be a derivative there, because if we think of that as the slope of this tangent line, it would be undefined. We could also have a discontinuity, and a discontinuity is never differentiable, even though in this one I have a slope of 0 on each side. Even though I have a slope of 0 on each side, if we think about the derivatives coming from limits, looking at a right and left-handed limit, well, the right and left-handed limits aren't going to exist. The reason being that if I'm taking my right value here, okay, I've got a solid dot here at 1, and I'm plugging that in, this is my f at 0. But on the left side, I'm plugging in my function that's on the left side. That's actually -1, and so as I'm approaching 0, those disagree. Now, if I want to find where a function is not differentiable, I have to look at some information from the graph. Now, notice in this one I've got x minus 2. I want to think about what this would do. Now, we noticed earlier that the absolute value function is not differentiable. Why? Because it has a corner there. I also recognize this is an absolute value function, so it's going to have the same corner somewhere. I just need to know where that corner is, so I'm going to take my inside of the absolute value and set it equal to 0, and we find that this is going to change at x equals 2. So at x equals 2, we're going to have a corner, and we say f is not differentiable at x equals 2. Now, one thing about differentiability is it basically says we're going to have a nice smooth curve. We're going to say it implies local linearity. What local linearity means, if we keep zooming in on our curve, you can do this with your calculator, then it starts to look less like a curve. If I zoom in close enough, my window on my calculator is just going to be a line. Now, if I took something like the absolute value function, no matter how much I zoom in, I'm still going to have a corner here. And so that would not have local linearity. But if I have a smooth curve, we will have that local linearity, which means the function is differentiable. Next, we're going to look at finding derivatives on a calculator. Now, the way your book is going to ask you to do this is they're going to say use ender, which is saying the numerical derivative. We're not really going to do it that way because there are more efficient ways to do it. To find a numerical derivative using our calculator, we're going to go, if we're using an Inspire, just go to Menu, you have a Calculus menu, and choose Numerical Derivative at a point. At that point, it's going to ask you for the variable you're using. You usually just use x, and then the value that you want to find the derivative at. So if I want to find the derivative at x equals 3, I just plug in 3 and say OK. At this point, I type in the function that I'm using. Say I'm using x squared, and just hit enter, and it'll give me the derivative at that point. If I'm using a TI-84, there's now a shortcut. If you go to your math menu and scroll down, you'll find the numerical derivative here. Hit enter, and notice the form is very similar to the Inspire. You need to tell it, though, the variable right here, that you want the variable x, and plug in whatever function. Let's use x squared again, so x squared. And then you'll need to go over here and tell it the value that you want. We want it at x equals 3, so we hit enter at that point. But we can't always trust our calculator to find the numerical derivative, because what a calculator does when they graph a line is they choose various values and then they connect the dots. And so they might not have necessarily chosen that point exactly here. So if they're connecting the dots, we might end up with a slope of 0 down here connecting the dots, even though it's really -1 on this side, 1 on this side. And at that point, our derivative should be undefined. So depending on how your calculator calculates that, you might get a wrong answer for that. And so we need to be able to do these by hand as well. Our next theorem says differentiability implies continuity. What this means is if we say that a function is differentiable, it means that there aren't going to be any breaks. If it has a derivative, it's continuous. We're not going to have any jumps. We saw a problem earlier where we had a jump, and so they couldn't agree on either side. It has to be a nice, smooth curve. And we also have then the intermediate value theorem for derivatives. Now we had an intermediate value theorem before, which said if we're going from A to B, we take on all values. But if we're talking about the intermediate value theorem for derivatives, what we're saying is if we look at A, okay, and we have a derivative of A, here in this graph, it looks like that slope there is about 4. Okay, I'll use red because we're talking about that red tangent line there. Okay, so I'm just going to estimate, say that that's 4. And over here at B, f prime of B appears to be about -1. So if I wonder, is there somewhere on that curve where I have a derivative of 0? Well, since it has to be a smooth curve and I have to take on all values from 4 to -1 and 0 is between 4 and -1, I know that somewhere in this interval from A to B there must be a slope of 0. Now I can see that right here. I could also use this for other values. We would know that there's a slope of 3, somewhere there's a slope of 1, somewhere there's a slope of -1/2. And so all those values are going to happen. Now the one condition, it has to be differentiable on that interval. We can't have any corners or cusps or discontinuities or any of the other kinds of ways that a function might fail to be differentiable. So we could ask the question, does the step function, any function, have this as its derivative? So if this function over here is f prime of x, this is our derivative here, we want to think about what that would say for our original function. Notice from 0 to 1, we have a slope of 0. Now we need to have a starting point. Here's a starting point drawn on here already. From that point, I know that I have a slope of 0. Now assuming that this is continuous, notice that suddenly I have a slope of 1. So I'm going up like that, and we can see right here this is not differentiable at this point because I have a corner. I would also have a corner at the next place and at the next place, and so this thing is not differentiable